Yeah, ladies and gentlemen, welcome to this 8th lecture on 3D coordinate systems. Today we will talk about an important application, namely robot arms. We want to model robot arms and describe their motion in 3D using what is called the Denavit Hartenberg parametrization, which is a special representation for kinematic chains, which are actually chains of motions which are described by their relative motions between neighboring frames. So let's start with some examples. You all know the relevance of robots in industry for assembling parts for building cars. You see here a video where you see sections of robots working on parts, working by taking the parts, putting at the right place, and you see they are working in parallel and of course replace human motion. The second example are walking or running humans or robots, and I show you an example for motion capture with a video camera from Hanover, which is shown here. So you see here the motion of a person, and if you have a look at it more in detail, you see here in red the skeleton, idealizing the skeleton of a human, and you see that this human is captured by a video system, and by analyzing these videos you can actually derive the skeleton, this idealized skeleton, and generate artificial views of the same motion of the human which you see here. And the last example I want to show you here is a robot which is jumping, making a roll first. And you would be happy if you would be able to do this. Sportive people can do this. And this robot weighs about 80 kilos. And obviously the company was not able just to assemble all these parts, but actually is very strong in the control of these motors, which actually control the different joints of this robot. The fourth example is about a very specific task, namely tunnel surveying. You all know the Gotthard tunnel, which is about 57 kilometers through the Alps, and they are boring the tunnel from two sides and hopefully meet in the middle, and this has to be done over 30 kilometers without having a reference to the outside directly. So the idea is actually you have here the tunnel boring machine, which cuts out the rocks in the Alps, and you have here a surveying technology which enables you to have a sequence of points, actually of course coordinate systems, which actually is tracked until to this point where the control of the boring machine is actually taking place. So this is a very specific type of kinematic chain, since it chains the individual coordinate systems here in 3D through the tunnel. So what are kinematic chains? These are chains of motions in a sequence. They are called kinematic because we only refer to the geometry, not to the dynamics. That means not the forces which are taking place there. And the sequence is described by relative motions, so only between them. So there is no external reference except for instance at the beginning. And as you saw for the skeletons of humans or robots, you have several sequences, like for the left arm or the right arm, or for the legs. Each of them is a sequence, but they are connected to a tree-like structure. And that means we would like to know how to model such robot arms. And of course, these robot arms are special kinematic chains, in contrast to the more general one where the motion can be arbitrary. So let's talk about how to represent such a robot arm, such a chain, using what is called the Denavit Hartenberg parametrization. So let's assume we have a robot arm, a passive arm, which is actually only used for measuring. I show you this immediately. This is an arm from the company Faro. It has 6 degrees of freedom. It can measure in a volume of about 1.5 meters and has an accuracy of 0.02 millimeter. I show you this now in a live demo with such an arm. So what you see here is a measuring arm. It's a passive robot because I control, as a user of this measuring arm, I control the motion. And you see I can move this measuring tool here, which is a ball, and actually touch, let's say, the surface here, and then the system is actually measuring the angles in these joints between these different links of the robot arm. I give you an example how to measure such an object. Let's say this part, I can measure in here, I can go down here, I can turn the measuring tool around and actually always measure from the inside. Or you have such an object where you want to measure the thickness of this part, and then you can actually go on the other side and measure the surface point from the other side. The technique is such that this measuring ball has a sensor which identifies that it touches a surface and then knows from which side, and then because it's a ball, it knows how to transfer the position of the ball to the surface point. Now, the question is, how many degrees of freedom, that means how many such joints do we need? So you see we can rotate here from the ground, which is, let's say, the system 0, we can already rotate this first joint. Now, the second part is this motion, around this axis. Then we have a rotation around this axis, which actually, this is fixed and this is moving. That means we have here a possibility to rotate around this vertical axis. And then we again have a horizontal axis, which you see here. Then we have here again a possibility to rotate on this axis. And finally we have again a horizontal motion of the, in this position, a horizontal motion of the final part where the measuring tool actually is connected to. Of course, this is not necessarily horizontal, as you see here, so it can go in any direction in 3D space. How many such rotations do we observe? So we start with this one, second, third, fourth, fifth, and sixth. So we have 6 degrees of freedom, so we need to fix 6 angles in order to come to a certain point. That means if we would know how this is constructed, that means if it is calibrated, we need to specify 6 angles in order to say where this point is. Actually, it's the other way around. We say where this point is and where it should be, in which direction, and then we can control the motion of the arm. And now you see what happens if we actually have a certain point here. We have a certain degree of freedom to reach the same 3D point here. So this is, let's say, our measuring position, and we can have it in reach it in several ways. Now, why do we have 6? Actually, if we would have 3D coordinates, 3 coordinates, we only would need 3. But if we do this, we are very limited. Let's assume we are only in this plane, and let's assume we have only 2 degrees of freedom. That means this one and this one. Then we can reach only a small area. So it is good to have a third rotation in this direction. The second is that we would like to measure a point not only from one side, but also from the other side. That means we want to specify not only the x, y, z coordinates, but also the normal of the measuring activity. So from here or from here. So we have 5 degrees of freedom, and if we would have only 5 degrees of freedom, that means 5 angles, we would be limited in the range of possible configurations, and this would be a little bit awkward to do the measuring easily. So this is the reason why Faro decided to make a 6 degrees of freedom robot arm to do the measuring. Now, how accurate do you think we can actually measure this? So this would be, say, the 0 point here at this place, on this ground plate. And how accurate would you think that we can measure a point in 3D? If you look into the specification of the robot arm, they say they can reach below 50 micrometer. This is a 20th of a millimeter and even better. And we will have to find out how this actually can be achieved. That means how accurate do the angles in these joints need to be measured in order to actually reach an accuracy of this quality. So this is what we want to discuss in the next few minutes. Thank you very much for this part. We now go back to the slides. So now I just showed you such a measuring device, a passive robot arm. And we now want to look how to model such robot arms. There are 2 basic types of joints which are very common. What we saw, that we have rotations around axes, which are called Revolut Joints. So if you have such a ball bearing, which is actually with small balls, very tight but very accurate put together, so that you can actually have a smooth rotation around a fixed axis. The second type of joints are what is called prismatic joints. There you only have a translation along a certain axis. Here you have an excavator which has 3 degrees of freedom. So you want to control this shovel. It has to have a certain position and a certain direction, which is 3 degrees of freedom. And you see here 3 hydraulic prismatic joints which control this excavator. There are others, of course, for instance, spherical joints like our shoulder. So we have the rotation in this direction, we have the rotation in this direction, and we have the rotation in this direction, which is the 3 angles which we know. And there are also cylindrical joints which have a translation and a rotation simultaneously. We only discuss rotations, that means only Revolut joints. So let's assume we have such a robot arm which has links which are joined by these joints which are revolute. That means have a rotation axis. Let's start here with the rotation axis z n minus 1. Then we have the next one, n, which is actually this direction, this rotation axis. Then we have a rotation around this arm, which is an axis which goes here through, which is Zn plus 1. And then we have a rotation around this axis, which is Zn plus 1, n plus 2. So the question is now, we would like to describe the relative positions, spatial positions of these rotation axes in 3D. How many parameters do we need to do the specification of a 3D line with respect to a coordinate system? So let's assume you have a coordinate system here and you want to specify this line in 3D. If I would be in class, I would ask the students to discuss this, and after a minute I would ask them what they think is the right number of parameters. I make a list of 3, 4, 5, 6, 7, and they have to choose and they vote, and then I ask them why they chose certain numbers. So take a look, stop the video, and think about how many parameters you would need. So you have made a decision, and let's go now to have a look at what a 3D line actually needs as parameters. And the result is the following. You have 4 degrees of freedom. That means you need at least 4 parameters to describe a 3D line. That's the minimum number. And in general, you can do this with 4, not in all cases. Now, let's have a look why this is so. So you have here a coordinate system x, y, z. You have a 3D line L here. And you can imagine that you intersect this 3D line with the xy plane, giving this point x, and the yz plane, giving the point y. And now you see that you need 2 coordinates, xy, for this point, and 2 coordinates for this point, yz. That means you need 4 coordinates to describe the position of this 3D line. It doesn't work in all cases. For instance, if you have a horizontal line, you have no intersection point with the ground plane, then you have to take a different one. Or you have an alternative possibility. So let's assume you project this line onto the xy plane. That means you get this line G here. And you can also project it onto the xz plane, which gives you this line F. And now you remember that you need 2 parameters to describe a line in 2D. That means you need 2 parameters for this line, and you need 2 parameters for this line. Then if you have these 2 lines, you just take planes which are normal to the xz axis through F, which gives you the plane A, and you take the plane which is normal to the xy plane through this line G, which is the plane B, and you intersect A and B, and you get the line. So how you look at it, there are other possibilities to describe it and to reason about it. You need 4 parameters to describe a 3D line in space. Now the question is, how do we describe a joint, let's say the nth joint, if the coordinate in the previous joint is given? So let's assume we have the previous coordinate system Sn-1 with its origin O(n-1), its x, y, and z axis Zn-1. And we have the new rotation axis here, somewhere. Yeah, so let's assume it's this way. We assume it's not parallel because otherwise we have to do special arguments. So the first thing is that we know from geometry, if you have 2 skew lines, that means 2 lines which are not intersecting and not parallel, there is a line which goes through these 2 lines which is perpendicular, which actually establish the shortest distance between the 2 lines. Now, if you look at this figure, you see that if you take this line and this line, you can imagine that the point here and the point here are those which establish the closest distance between these 2 lines. Now, the definition of the coordinate system in the new frame n on this line ON is given by this point, which is closest to the Zn-1 axis. So we have the point. And then we have to fix the coordinate system. Of course, we have the z-axis. We always rotate about the z-axis. And then we say we have the x-axis, which is along this direction, which is the shortest distance, and pointing away from the old z-axis. So we have the x-axis and the z-axis, and then we of course have the y-axis making a right-hand system. So we have this way, and this way. So we have these three coordinates, x, y, z. So this is the definition of the new coordinate system, and now we want to describe how this in terms of 4 parameters. The principle is that we take this coordinate system, Sn-1, and move it into this coordinate system in 4 steps. The first step is we rotate this system around its Zn-1 axis by the angle theta n. That means the xn-1 axis moves here. This is actually also the direction of the xn axis. So this is, so to say, the first rotation. So the Zn-1 axis stays, the xn-1 axis rotates into this direction, and the y-axis in this direction. So that's the first parameter. That's the theta n, which is actually that what we later use for describing the motion of a robot arm. The second one is that we shift this rotated coordinate system, x, y, z, along the z-axis by the amount d, n, in order to define the height of the origin ON over the original xy plane. That's the second motion. The third motion is we need to specify how far this origin is from the z-axis. This is the parameter an, and by definition it's a positive value. And that means up to this point we have fixed the origin ON in this original coordinate system. Now what we have achieved is the following. We have the x-axis going here, the z-axis going upwards, and the y-axis being horizontal, parallel to the xy plane before. That means we still need a rotation of the z-axis from this direction into the actual z-axis which we want to achieve. That means we have a rotation around the x-axis. Now if you look at the 3 transformation matrices, you have here the first motion, which is a rotation around the z-axis, Rz by theta n. Then you have a translation in z direction by dn. Then you have a translation in the x direction by an. And finally, we have a rotation around the x-axis by alpha n. Now, each of these motions is described in the previous coordinate system. So we have to concatenate them, we multiply them, and because this is case B, we have the description of the motions in the local system, we can describe the complete motion by 4 parameters, by multiplying the first, the second, the third, and the fourth motion, multiplying from the right, and we get the motion from the coordinate system Sn-1 to the coordinate system Sn. So this is an active motion of the coordinate system. The coordinate system after the motion is a different one. So we call it Mn, and it depends on 4 parameters, which are these 4 values. And if you multiply these matrices out, you get this expression. Of course, we see that we have zeros here in the last rows and a 1 here. It's a motion matrix, so this should be a rotation matrix, this 3 by 3 upper part. And here we have the translation vector. You see here the dn is just the motion in the vertical direction, and the an is in the direction of the theta. And we see that the z-axis is not influenced by theta. So here we have only alphas. we will use this later. Now, what is this motion also, this matrix also doing? It's actually also transforming the coordinates of a point in the new system into coordinates of the old system. This is a coordinate transformation. So we can take this matrix. Let's assume we have just a translation, or everything else is 0. Then the coordinates are increased. That means the dn, let's say here, is positive. That means the z coordinates of this vector is increased by d to get the previous one. So we can actually take this matrix as the coordinate transformation from n to n-1. Here the point is the same as here, only described in 2 different coordinate systems. You remember this notation that we have here the motion of the active motion of the systems from n-1 to n, and we know that the coordinate transformation with the same parameters is that in the reverse order. That means from n to n-1. So we can use this matrix for 2 purposes, either for the motion of the coordinate systems or for transforming coordinates. We will use this in the following. So how do we modeling now the whole arm? So we have Revolut joints. Then, of course, theta n, which is an angle, is measurable, as in our case. Or if you have an active robot, it's controllable. That means you can steer it by some motor. Or you have a prismatic joint, then you have the dn, which is along the z-axis, which is measurable or controllable depending on whether you have a passive or active arm. The other 3 parameters have to be calibrated. That means you calibrate the system. That means you know these lengths, let's say A and D, and the alpha, and then you know how the robot arm is configured, and then you can describe the position, the pose of the robot in 3D by just fixing the sequence of the theta n's. Now, again, you start with the first system, 0, and transfer this coordinate system until to the end. That means you actually multiply these matrices, which depend now only on theta 1, because we assume that the other parameters are fixed. That means we have a product of all these individual motions, in our case 6, from m1 to m6, depending on the 6 angles which we can measure in the system. And this gives us the possibility to describe the motion of the original system, which is actually the platform of the robot, which is fixed, into the coordinate system of the end effector, where we actually have our measuring tool. We also can have a combined coordinate transformation. Let's assume we have the end effector of my finger. Yeah, we need to describe the position of this point in this local coordinate system. So this is this one. This is about, let's say, 15 or 20 centimeters. And then we can use exactly the same product to describe the coordinates of this end effector, the measuring point, in the original basic system. So you see, this product of matrices can be used either for the active motion of the coordinate systems or for the passive coordinate transformation of our end effector. Now, this is a description of the faro measuring arm as you saw it just now. So you have here the basis. You have here the first link, the second link, the third link, the fourth link, the fifth link, and the last link to the measuring point here. You see that the first link can be rotated by 360 degrees. This part can be, let's start here, up here. So this last part can be rotated from vertical down to this large angle by 164 degrees. And the same here for these two. We have 164 degrees where the arms can be tilted, and we have a rotation about 360 degrees in the vertical axis. And we will discuss the coordinate system. So we start here with the coordinate system 0. We have a coordinate system here for the motion, the rotation on this horizontal axis. We have here the rotation on the vertical axis. We have here the rotation about the horizontal axis, here the axis, etc., until to the final point. We will go into this more in detail. So, how is this arm described? These parameters, theta, d, a, and alpha, are what is called the Denavit-Harten parameters. And depending on the degrees of freedom, we have here, in this case, 6 of these sets of parameters. So we have here 0, 360, 90, so etc. And I didn't give the numbers here, which describe actually the complete arm. And you can imagine that if the arm is vertical, then all these angles, theta, are 0, or depending on the direction, 180 degrees. And these values here in millimeters say how far are the how long are the lengths. So for instance, here you have 300 millimeters, here you have 600 millimeters, here 600 millimeters, and the offset between this point and the axis here is 60 millimeters. So you find these values in millimeters in this table, and these values here and these 3 rows, D, A, and alpha, need to be calibrated, and these values D, N can be measured or controlled if this would be an active arm. So let's make an example. We start here at the ground of the table where the robot stands, and I assume that this can be rotated. That means the coordinate system S0 is chosen so that the z-axis is actually the first rotation axis along which we rotate at the beginning. So this is a vertical rotation in z-axis, and of course we choose x in some direction which is comfortable, which is in the 0 situation parallel to x1, and then the y-axis is going downwards. So we have x, y, and z going upwards, which is the S0 system. Now, that means the z0 axis is this vertical line. Now, what is the z1 axis? This is a horizontal line which either goes into the screen or out of the screen. You can choose one or the other, it doesn't matter. So I chose that the axis goes out of the screen. So you see here, if you go close, you see here a black dot, which is actually showing the tip of an arrow. If the arrow would go into the plane, I would show a cross, which shows the feathers of the arrow from the behind. So this is a horizontal line, which has a direction out of the screen. So we need to know where is the origin of this first system. So we have a vertical axis like here, and we have a horizontal axis like here, and of course we have here in this horizontal direction the point which is closest, so this would be this point here. So O1 is in the height, of course, of this axis and closest to this. Now, we start with theta. Theta is the angle which we need to rotate to come from the x0 axis into the x1 axis. Now we have chosen them that they are parallel, so the theta 1 is 0. So this is easy. The second one is the shift of the coordinate system from 0 to 1, which is this 300 millimeters, which is this value. then we have to move the coordinate system from here to the right in the direction of the x-axis, which are these 60 millimeters. Now what we have is a coordinate system which is x, y, and z. And we need to have this vertical axis in the horizontal. That means we have to rotate around this x-axis by 90 degrees, which is this 90 degrees. So the first 4 parameters are understandable. Now we go to the second axis. Now we have a rotation again in the vertical direction. That means actually the z0 and the z2 axis are the same line in 3D. So the origin of this second system will be at this green point. So these 2 points are actually those points which are sitting on the line closest to both lines. So this is the origin. Now the first thing is that we need to rotate this axis into this axis, and we need to rotate around the z-axis. So we have the z-axis horizontal, the x-axis horizontal, the y-axis vertical. And in order to do a rotation, we need to rotate around the z-axis in order to get the x-axis in the other direction, which is a rotation by 180 degrees. Whether you take plus or minus doesn't matter, of course. So the first angle is 180 degrees. Then we need to change the coordinates in the z direction by d2. Now these are at the same in the, let's say, the plane of the drawing. So we have, of course, we have no shift in z direction. And we have a shift of 60 millimeters in the new x direction. In the new x direction. We always refer to the last coordinate system. Now what we have now is that the x-axis is like, what do we start? Like this. So the z-axis actually points outwards. So what we need to do, we want to change this axis into the vertical. That means we have to make a rotation by 90 degrees around the x2 axis, which is this angle 90 degrees. So this way you can go through all the 6 coordinate systems. And of course, at the end, we have the transformation between this coordinate system and the coordinate system of the measuring part here. So we will have a certain degree of freedom here with the definition of the coordinate system in this part. So this was the description of a robot arm using the Denavit Hartenberg parameters. So let's have a little bit more general look at kinematic chains. What did we say? Kinematic chains are sequences of motions. These sequences are described by relative motions, and we might have trees as sets of sequences. So let's assume we want to model a kinematic chain. I now start from the end effector of the, let's say, arm. I change the notation that it also may mean time. So this is the last link. So we have, so to say, the coordinates described in the last effector. So we have these, what was it? We have here a distance of 170 millimeters. So we need to have this point described in this local coordinate system, let's say 0, 0, 170. So this is this point. And now we model the motions backwards from t equals capital T to t equals 0. And that means we have a recursive definition of the coordinates in the following frames. So we have the coordinates in frame t, multiply with the corresponding motion matrix, and get the coordinates of the same point in the previous frame. And you see these are coordinate transformations, so the indices are going from lower index to upper index in order to be able to this. So this shorthand notation actually means from t to t-1. We will use this. I just omitted the upper left index in order to have a shorter notation for the longer products. So if we just want to know the coordinates of point x in frame 0, that means in the ground plane, we need to multiply the point described in the last frame from left multiplied with mt, mt-1, etc. until m1. So we could also take the product and get the motion from capital T to 0. And the question is now, why I write this down, is I would like to know how accurate is x in the 0 system. If these coordinates are uncertain, or if the motion parameters in this sequence of these motions are uncertain. That means we need to have the Jacobians of x0 with respect to xt and with respect to the parameters of these individual motions. And I put out this motion mt extra because we have to look at that. That means we would like to have the Jacobians of x0 with respect to xt and with respect to all intermediate motion parameters st, which are the rotations and the translations, that are 6 parameters. Now the Jacobian with respect to xt is easy. So we have just x0 is this matrix multiplied with xt. So actually this motion matrix is the Jacobian of x0 with respect to xt. So this is easy. We directly see this. Now we look at the effect of the teeth, small teeth, motion onto the x0. So we describe the motion by mt and its uncertainty by the covariance matrix of dr dt, that means by ds. Now let's have a look what happens here. So we take the total differential of d of x0 only with respect to the motion t. All the other parameters are assumed to be fixed for this analysis. So we have here the coordinate transformation from system t-1 to 0. And if we multiply this out, we have here the coordinate transformation from t-1 to t. That means if we multiply this out, we actually get the xt. Okay. Now, what is dmt? There we have to go back to our last lecture and look how to differentiate motions. And we remember that the differential of a motion, that means the change of the motion matrix due to the change of the parameters s, is the motion itself multiplied with the differential of the motion at point 0. And this matrix actually was the skew-symmetric matrix of the small rotation and the small translation. So now we can plug this in, this expression, into this matrix, in this product. Now let's have a look what happens for the total expression. We take the differential of x0 as the product of the coordinate transformation from t-1 to 0, then the differential at 0 for the small change of the parameters, multiplied with what? Now we have here the xt, and we have to multiply the whole thing with the coordinate transformation from t to t-1. That means we get here the coordinates in frame t-1. Okay, this is the m from t-1 to 0. then we get this differential motion at 0, which with a skew-symmetric matrix and dt, which depends on S or R and T, and the coordinates, homogeneous coordinates here. Now here we have the non-homogeneous coordinates of the point X in frame t minus 1, 1. Now we want to have it on the right side, so we do the same thing as before. We take here the cross product of dRt with x t minus 1, which is the negative cross product of x t minus 1 and rt. And we have here the differential change of the translation. And that means this part here, from here to here, is the Jacobian. That means the Jacobian of our coordinate in frame 0 with respect to the parameters at time t is this coordinate transformation from t minus 1 to 0 multiplied with this skew-symmetric matrix, unit matrix 0, 0. Now you see that here is actually the coordinates of xt minus 1, which is actually the lever arm which makes the influence on the coordinates. So if there is a motion in this t, we have let's say a rotation, only the rotation part, and this is multiplied with the length to the beginning, xt. Okay, and now what we can do now is, of course, do the variance propagation, because we have now the Jacobians. So the covariance matrix of the end effector coordinates, the last coordinates x in the reference system x0, can be derived under the following assumptions easily. We assume that the relative motions are mutually independent. That means we have measurements which are independent. In the case of a robot arm, we assume that the measurements of the angles are mutually independent. Then the relative motions are independent on the starting point. That means the coordinates of the end effector, that in the last coordinate system, these are independent. And we assume that the calibration is perfect, or the errors of the calibrations are negligible. And then we just have to do the variance propagation. We get the Jacobian with respect to the coordinates, which is this one, multiplied with the coordinates of the point in the last system, plus the sum of all the individual components using the Jacobians, multiplied with the covariance matrix of the parameters at the tth frame. So this is the way how you could derive the covariance matrix of the point at the end of such a chain in the coordinate system at the beginning. Now, how does this look for the robot arm? There we have a little bit special situation, because we have only one parameter per individual joint. So we just have to differentiate this 4x4 matrix, which we derived previously, with respect to theta. Okay, we remember there are zeros here. There was a 1. 1 is constant, so the differential is 0. Then we had here in this row, we had sine and cosine alpha, which is not dependent on theta. And that means we only have values in the first two rows, which depend on theta. That means the Jacobian of this motion matrix, this is a matrix 4x4 with respect to one parameter, is actually this 4x4 matrix. So how is the relation? We have the coordinates in the nth frame. We have the transformation, coordinate transformation from n to n minus 1, depending on theta, gives us the coordinates in the nth minus 1th first frame. And if we take the differential, we see that the Jacobian is nothing else than this matrix. And then, of course, multiplied with all the transformations which we need to come to frame 0. And multiplied with xn. So we have now a very simple situation. that we have the Jacobians of our coordinate of the end effector in the system 0 with respect to all the individual angles. In our case, this would be 6 angles. Okay, let's have a demo and have a look. I show you here a animation. So you see here a plot of the foul arm. Here you have the basic coordinate system. You see here the first link, the second link, the third link, the fourth link, the fifth link, and the final link with the measuring point. And what you see here is actually the covariance matrix, the uncertainty ellipsoid, with which you can measure that point in 3D in that situation. So is that reasonable? Let's have a look. So let's have a look from the side. So we have here the whole arm standing straight up. And of course we have especially angles, uncertainties here around this rotation, around this joint and around this joint. And of course, if you have an error here in the angle, then the lever arm is very long. That means you have a high uncertainty in the horizontal position. That means in the x coordinates. If we look from the other side, we see that now we look along the arm, which could be bending downwards, and we see that the uncertainty at the measuring point in the direction, the y direction, is very small. That means the ellipsoid, which describes the uncertainty of the 3D point, is very elongated. I showed you here the accuracy in millimeter. You see here the accuracy is about 0.06 millimeters. And the ratio between the large and the small semi-axis of the ellipsoid is about 8, which is quite large. Now let's go back and make a rotation around this second axis. So we change this axis here. Now you see that the robot arm goes down here, and we have now here an angle of around 32 degrees. Now we change, rotate the axis around here. So. And finally, we do the same thing with the final horizontal axis. And you see we have a configuration which we can imagine that can be realized, and we obtain an accuracy of 0.03 millimeters. That is half the standard deviation which we just found. And this ellipsoid here is quite round. It only has an offset of about 1.5. We can see this if we rotate the whole arm around the vertical axis. You see that the uncertainty ellipsoid is quite round. Okay, now let's look what happens if we rotate one of the other axes. No. So now we rotate around here. So now you will see we rotate around this joint. That means we have rotate around this axis. And we can rotate around this axis, which is now horizontal. Now let's see what happens. Yeah, now that means we can actually simulate all these situations, and you see that the uncertainty now is a little bit off. We can rotate this and have a look at this, how the arm looks like. So this shows you that by using the equations which I showed you before, we are able to predict the uncertainty of the measuring possibilities of this arm in a certain configuration, and we have seen that the configuration, of course, makes a difference. So if we would rotate down, let's say we try to put this point quite close to the point. Now we do this. Now we change this. Now we have this. And now we rotate around this joint a little bit further. And come very close to the beginning, to the origin, and you see the accuracy is also quite good with 0.03 millimeters, because this point is very close to the original coordinate system S0. That means an effect in the error of joint 2 only has a small effect, because the lever arm here is only very short. So, just to recapitulate, so if the arm is just straight looking upwards, we assumed an accuracy of 0.0022 degrees, which is what the Faro description says. And we obtained an uncertainty of about 0.06 millimeters, especially in this direction. And the condition is about 8. That means the ratio between the maximum and the minimum standard deviation at this place is about 8. If we have a situation which is a little bit more complicated, we of course can reach better accuracies, and we can also find out that the uncertainty variation in the different directions is much smaller. I give you here stereo images, which you could then look at if you know how to do it. This is from left to right, so the left figure you look with the left eye, and the right figure you look with the right eye. So if they are close enough, you just look at infinity, and then the two images merge. There's a description in this link how you can do this. And if the images are too far apart, we cannot move our eyes outwards, so we cross the eyes and look to the left image with the right eye, and to the right eye to the right image with the left eye, and get a stereo impression. So this was what I wanted to show you today. What we discussed was how we model robot arms with kinematic chains, especially the Hartenberg parametrization, where we need 4 parameters per link. 1 is observable in this case, or controllable if you have an active arm. And we had a look at the variance propagation through kinematic chains in order to be able to predict how accurate we can actually do the measurements. This closes this lecture. Next time we will go back to spatial transformations, similarities and motions, and look how we estimate parameters from corresponding point pairs. Thank you very much.